Alright, so this is the lab practical section for computational chemistry for experimentalists, module number 7 on vibrational frequencies and vibrational spectra. Today we're going to work through how to calculate and examine the vibrational frequencies and force constant of carbon monoxide and of a polyatomic molecule. So I've logged in to one of the remote desktops, and I'm going to execute some commands in a way that makes sure I can do more things from Gauss view. Here's my remote desktop. I'm going to open Windows PowerShell. I'm going to set the environment variable. env Gauss exedrr equals C:G16W. Now I'm going to run from the terminal CG09W GView, and that's going to run Gauss view. Going to give me a couple of error messages that I can just ignore. Now my first step is going to be the vibrational spectrum of carbon monoxide. You can calculate and look at the bond force constant and compare it to experiment. And you can calculate a model infrared vibrational spectrum that's a pure vibrational spectrum with no rotational splitting. We can talk later about where you can look into how to add the rotational peaks. So first we've got to build the molecule. CO is a carbon bound to an oxygen. When I build it this way, I have an extra hydrogen atom that I have to delete. I'm going to set up the calculation and run it from Gauss view. I'm going to do an optimization plus vibrational frequency. Rather than using our default Hartree-Fock theory, we're going to use B3-lip DFT, because now we've talked about what these different DFT methods are. We've talked about what the different basis sets are. This is a good standard choice. The molecule is going to be a ground state neutral spin singlet. I'm going to submit this through Gauss view, save everything in here, overwrite that, run the calculation, ignore the log file. When my calculation runs, I'm optimizing the geometry, which is straightforward. I just have to optimize the CO bond length. Once I'm done, I run a second calculation at that optimized geometry. That's vibrational frequency. It takes a little while to compute the vibrational frequencies. Things are done there. I'm going to open the checkpoint file, because now I know where all my environment variables are. I can format that checkpoint file automatically. Here's my optimized carbon monoxide. I'll use my little inquire tool to say the optimum CO bond length at this level of theory is 1.13726 angstroms, which is pretty close to experiment. If I look at my results, I have now it's no longer grayed out this section on vibrations. I'm going to run freak check, that's fine. Convert the information in the checkpoint file into computed IR spectrum. This computed IR spectrum is really one line, one pure vibrational transition that's broadened by an empirical broadening. If we look at the high-resolution experimental IR spectrum of carbon monoxide, what you have is no peak here. You have a peak here and a peak here that are combined row vibrational transitions, and the width of those peaks is going to change based on the temperature. But we're not doing any rotation. We're looking at a pure vibrational transition. Well, what can we see? We can see the computed vibrational frequency is 2202.7 wave number at this level of theory. I can find other information if I look at the log file. So if I just go and examine co.log. Open it in Notepad and I start scrolling down. I have a bunch of stuff about basis set, geometry guess, geometry optimization. Now I start a new vibrational frequency calculation. And down at the end I get my information about the vibrational frequencies. So I can talk a little more about this. You can see this line that says low frequencies. And we talked about this briefly when we talked about transition states. This molecule has 3 atoms, each of which has an X and Y and Z position. So if I look at, I have actually 6 different degrees of freedom. 3 correspond to translation of the center of mass, 2 correspond to rotation, and 1 corresponds to vibration. When I do this calculation, I build the whole 6 by 6 dimensional matrix of second derivatives of the energy with respect to positions of the atoms. I diagonalize that matrix, I get 6 eigenvalues. In a perfect world, I'd have 3 that are 0 for the translations, 2 that are effectively 0 for the rotations, and 1 non-zero one that's a vibration. Here, because I did a numerical calculation, not a perfect one, I get some numerical error. I get 3 very small vibrational frequencies that are not really vibrations at all. They would be 0 if I did a perfect calculation. They correspond to center of mass translation, 2 from rotation, and this is the frequency in wave number of the harmonic vibration. Here's the force constant in millidyne per angstrom, when you can convert that to kilogram per second squared or newtons per meter. And so that's the number that you can compare to some of your other results. That's the number that you can compare to some of the things that you came up with in part 1 of the lab. So I'd like you to have a table that has things like the computed vibrational frequency, the computed force constant, and then the force constant that you extracted out from the experiment. How good of a job do we do reproducing that? Make sure everything's in the same units. And that is a diatomic. Now what about a more complicated molecule? For a more complicated molecule, you can still predict the vibrational spectrum. What I asked you to do in the lab is I asked you to design an experiment that involves an enol to keto tautomerization, and you want to say, given the experimental spectrum, what is the ratio of enol to keto present in your system, and what is the delta G, the experimental delta G of enol to keto? So that's going to involve computing the spectrum of 2 different isomers, looking for differences, and then fitting to the difference. So I'm going to illustrate this, first of all, with a fairly simple enol to keto tautomerization. So we're going to do a simple molecule in a new calculation. And we're going to do a related tautomerization. This is one that I like because we've looked at it in some other places. It's similar to what we did in the transition state problem. So we're going to look at thioformic acid. Okay? So here's 1 tautomer of thioformic acid with a hydrogen on oxygen. We're going to set up a calculation using, now here I'm going to use B3-lip DFT again, because it's probably more reliable than Hartree-Fock theory for this problem. We're going to do an optimization and vibrational frequency calculation. FA, and we're going to do the hydrogen on oxygen tautomer here of thioformic acid. Now, for this molecule, I have 1, 2, 3, 4, 5 atoms 5 times 3 equals 15 different degrees of freedom. 3 will be translational. 3 for this nonlinear molecule will be rotational. And so I'll have 15 minus 3 equals 9 vibrational frequencies. So if I look at an infrared or Raman spectrum, I should have 9 different peaks in it. Some of those peaks will have nearly 0 intensity, but I will have a list of 9 of them in my plot. This calculation takes a little while on a desktop, so while it's running, I'm going to set up the other tautomer, where the proton moves from oxygen to sulfur. Use this clean tool to pre-optimize the geometry. Do the same level of theory, same optimization frequency, same DFT approximation, same basis set. I'm going to save this as a different file, TFASH. It's going to ask me if I want to submit the following file to Gaussian. I'm going to have to wait. I'm going to have to wait because I can only run one instance of Gaussian at a time. So we'll just cancel that and wait for this guy to finish. Alright, so we found the optimized geometry. Now we're running link 1002. It's calculating the second derivative matrix, the second derivative of the energy with respect to all the possible Cartesian coordinates of all the atoms. So with 5 atoms, 3 coordinates per atom, I get a 15 by 15 matrix that I diagonalize, and I get my 15 vibrational degrees of freedom. 3 should be 0 because they really correspond to translation. 3 should be effectively 0 because they really correspond to rotation. And the remainder are vibration. So as this runs, we finish computing the 2 electron integral derivatives, and we're done. I'm going to open the checkpoint file. There's my optimized geometry of the OH protonated tautomer. While I wait, I'm going to submit this job. So the SH protonated tautomer is going to run. And while I do that, I'm going to look at the OH protonated tautomer. I'm going to run freak check. And there's my results. Now I made one mistake, that I didn't have the Raman intensities computed. I think you need FREQ equals Raman to make that happen. Or you could do the optimization in one file and then take the optimized geometry and do FREQ equals Raman in the next file. So that's easy enough to do. But this is what I get. I get a predicted infrared spectrum. And if I look at this predicted infrared spectrum, it's got various predicted pure vibrational transitions. In a real molecule, these would be rho vibrational transitions, and they'd be broadened, and there'd be all kinds of anharmonic effects and other complications that we're not going to talk about right today. So in the gas phase, the first vibration is predicted to be bending. This other intense peak is it's hard to see until I tilt the molecule, but it's an OH wagging. It's a bond torsion. Here's another torsion. Here's some single bond bending and stretching. And I get a little peak over here in the formaldehyde, and I get a very, very intense peak right there, predicted to be at about 3700 wave number. That's the OH stretch of thioformic acid. So what that tells me is that if I look in this region, there's only one peak in the vibrational spectrum, and it's an OH stretch. So if I was looking at a gas phase IR spectrum of this molecule, I'd see one peak in this high wave number region that's the OH stretch, because there's no other very, very high wavelength peaks like there. I have a CH stretch here, but I have a spectroscopic handle that's this OH stretch. Now, as this calculation runs, I'm also going to see the corresponding IR spectrum of the SH molecule, which we'll get to look at in just a minute. So I'll stop the animation here, close this guy down, and just wait for things to finish, because my SH tautomer is almost done. Just a couple more integral second derivatives. It'll build the Hessian, it'll diagonalize it, and we'll get the predicted peaks. Just as an aside, look at this list. I have 1, 2, 3, 4, 5, 6, 7, 8, 9 vibrational nodes. And if I looked at the log file for this molecule, I'd have 15 quote-unquote vibrational peaks. The first 6 would have very, very low, almost zero frequencies, because they wouldn't correspond to vibration. They correspond to translation of the center of mass, rotation about the center of mass. So we'll open this SH protonated tautomer, move it down here. So, okay, what do we see? We have OH protonated and SH protonated. I should have a prediction of the tautomerization energy from these calculations as well, because remember, I computed the energy and the Gibbs free energy of this tautomer and that tautomer, so I can compare the two. With this one, I can go to my results, look at my predicted vibrational spectrum, run freak check. Here's my predicted IR spectrum. And now this is nice. Look at this. The OH protonated tautomer has an OH stretch at almost 3,700 wave numbers predicted, which you can see right here in the spectrum. The SH protonated tautomer, the low frequency part of the spectrum, looks about the same as the other tautomer. But now, there's some changes in the low frequency region, but here's a big change. That peak at 1,700 wave number is a CO, almost a, now it's drawn with one stick, but that's really, you could think of that as a double bond. And out here, the OH stretch, and where is that SH stretch? So surprisingly, two things. First off, my SH stretch is at a much lower frequency than the OH stretch, which is what you would expect. OH stretch is predicted around 3,700 wave number. SH is predicted around 2,700 wave number. So a big difference. Second, the OH is predicted as strong and very intense. The SH is predicted as not very intense. But I do have this diagnostic peak occurring at about 1,700 wave number that's mostly a carbon-oxygen stretch. It has some other bond-bending components. There's no such thing as a pure bond stretch in a polyatomic, but it's mostly bond stretch. And so now if I wanted to design an experiment, I'd say, well, all of my intensity in the region above 3,500 wave number is predicted to come from the OH protonated tautomer, from the OH stretch. All of my intensity in the region between about 1,500 and 2,000 wave number is predicted to come from the SH tautomer, from the carbon-oxygen, quote-unquote, double bond stretch. So I have two spectroscopic handles that I can use to determine the relative amounts of this species and this species. Now, it takes a little bit of extra work because I have to do normalization. I have to say what are the relative peak heights. It takes a little bit of extra work to make sense of that, and that's the thing that I'll ask you to do in the lab report, but you should be able to get something working. So, take-home messages from this. This is how to set up the calculations. It's how to read. I talked about how to set up the calculations. I talked about how to read the log files. I talked about how to view them in Gauss view by First you have to set that environment variable, then run Gauss-V from the terminal window. I mentioned the difference between pure vibrational spectrum and the rho vibrational spectra that you really see. I should mention again, and I emphasized it, but I didn't emphasize it quite enough, none of these peaks are pure bond stretches. Even this OH stretch has a little bit of component of other vibrations. This CO stretch has a lot of component of other vibrations. Anytime you describe one of these stretches, you just sort of describe it in a fairly hand-waving qualitative sense. But that should be all that you need to finish the lab report.